Before I begin, I'd like to make a quick disclaimer. I was not involved in any of these projects, and everything I share in this presentation reflects solely my own opinions and interpretations. This presentation is completely independent of these projects and does not represent the views of those associated with them. Furthermore, I want to quickly mention these disclaimers. You can see the key points on the slide. If you'd like to review the full details, feel free to take a moment to read through this slide. Recently, Eurocode 8 has explicitly introduced target reliability for seismic actions, a detail that was not explicitly stated in the first generation of the code. In the supporting document for this version of Eurocode 8, reference is made to the RINTS project and its findings. In this video, I will provide a short overview of my presentation on this topic. I will begin with a brief comparison between the target reliability mentioned in ASCE 7 and Eurocode 8. Then, I will examine the supporting document and its key contents. Next, I will explain some fundamental concepts in clear and simple terms, including fragility curves and hazard curves, which are essential for advancing this discussion. The core of my presentation focuses on explaining the RINTS project in detail. Finally, I will discuss recent research that builds upon the project's findings and explore potential directions for future studies based on ongoing research and their findings. ASCE 7 has long established a target reliability for seismic design, specifying a value of 2 × 10⁻⁻⁴ for risk category 2 buildings. In the second generation of Eurocode 8, the same target value is now explicitly mentioned. Additionally, ASCE 7 defines other conditional targets that become important in risk-targeted calculations. For example, it states that the probability of collapse should not exceed 10% in the event of a maximum considered earthquake, MCE. Recently, the Joint Research Centre, JRC, of the European Commission published supporting documents related to target reliabilities in Eurocode 8. Let's take a look at what is included in these documents. First, it is important to distinguish between the approach for regular loadings and seismic loads. For non-seismic loads, partial factors are calibrated to achieve the target reliability. In contrast, for seismic loads, the focus is primarily on the behavior factor, overstrength, and system detailing. Now, in the seismic section, this document refers to the findings of the RINTS project, stating that the observed seismic reliability indices for code-compliant buildings range from 2.9 to 4.3, with an average of 3.5. This corresponds to a target reliability of 2 × 10⁻⁻⁴. Before diving into the RINTS project, let me take a step back and briefly define fragility and hazard curves in simple terms to ensure everyone is on the same page. For those who are already familiar with these concepts, you may proceed to the next section. I have made several simplifications in defining the fragility curve for the sake of clarity, which might not sit well with some earthquake engineers. Simply put, a fragility curve indicates the probability of a structure exhibiting a certain behavior when subjected to an earthquake of a specific magnitude or intensity. On the other hand, the hazard curve tells us the quote-unquote probability of experiencing earthquakes of different magnitudes at a specific site. And yes, probability is not the same as the rate of occurrence. By now, you've probably figured out how we're going to proceed. Simply put, the hazard curve tells us the probability of experiencing a certain earthquake, while the fragility curve tells us the probability of a structure exhibiting a specific behavior if that earthquake occurs. So, if we sum all these probabilities for every possible earthquake expected at our site, we get the rate of observing that specific behavior. In technical terms, this process is called the convolution of hazard and fragility. Although the concept of convolution and the triple integral in performance-based earthquake engineering are not exactly the same, you can observe some similarities. These parallels can provide useful insights into their applications and interpretations. If we refer to the triple integral of performance-based earthquake engineering, PBE, these are the first two terms. Understanding these two is sufficient for grasping the RINTS project. However, later, we will see how introducing the third term changes our perspective. I will discuss this further in the Way Forward section. Now, let's jump into the exciting part. In this short version, I will skip some background details about the RELUIS consortium, the structure of this project, and its sister project. Instead, after covering some key aspects of modeling, I will focus on the main findings and reliability trends. In this project, 3 sites were selected to represent different levels of seismicity: Milan for low, Naples for moderate, and 𝗲𝗂𝗃 for high seismicity. Hazard curves for these sites were then obtained, followed by a disaggregation of hazard analysis. We will see that this disaggregation plays a crucial role when selecting time histories. The project considered 5 different building types. However, here we will focus on cast-in-place RC buildings and masonry buildings. For RC structures, 15 archetypes were evaluated, and for masonry structures, 6 archetypes were analyzed. To account for uncertainty, researchers selected 11 random parameters for RC buildings and 6 random parameters for masonry buildings. Among these, 4 parameters for RC and 3 parameters for masonry were specifically related to plastic hinge behavior and the force deformation law of structural elements. They then defined a large correlation matrix to account for various dependencies between these parameters. This matrix considered 3 types of correlations. 1. Inter-element correlation, between floors, which defines relationships between elements on different floors. 2. Inter-element correlation, within the same floor, which defines relationships between elements on the same floor. 3. Intra-element correlation, which defines relationships within a single structural element. Please note that in this project, a one-to-one association was used between structural model realizations and ground motion records. In this project, 200 pair of hazard-consistent time histories were selected through a systematic process. It began with hazard disaggregation, which helped identify the key earthquake scenarios influencing the site. From there, a conditional spectrum was derived, then using 𝗥𝗲𝗃𝗃 and Italian accelerometric archive databases, ground motions were selected. To ensure these records remained hazard consistent in terms of magnitude and distance, a post-processing step was applied. Then for computational efficiency, the length of time histories were reduced to 99.9% significant duration. Finally, these refined time histories were used to drive fragility curves for different damage states, focusing on usability preventing damage, UPD, and global collapse. Now, let's examine the findings. As you can see, seismic reliability decreases by 2 orders of magnitude as seismicity increases. It's important to remember that these results apply to code-compliant buildings, meaning that structures in higher seismicity regions are already designed to withstand stronger earthquakes. However, when we compare these findings with the target reliability specified in the code, the results are not as drastic. Only for certain types of buildings in high seismicity areas do we observe unacceptable collapse rates. When we compare the exceedance rate trends between collapse rates and usability preventing damage states, these findings open up a new perspective. Let me ask you, what do you think is most important when considering post-disaster recovery? Can we infer UPD rates from collapse rates? And what implications does this have for seismic design for resilience? Now, let's move to the way forward section, where we introduce the 3rd term of the PBE triple integral. This term connects or probability of a structure exhibiting a certain behavior to decision variables. The exciting insight begins when we explore which decision variables to consider, as they will shape how we assess and manage seismic risk moving forward. There is one interesting study on the fatality risk of code-compliant buildings built upon the findings of this project. It highlights that while fatality risk varies with seismicity, it remains lower than other common causes of death in Italy, such as diseases and accidents, which is reassuring news. However, what do you think will happen when we introduce equity considerations? And finally, would it be economically viable to increase target reliabilities if we consider the entire life cycle cost and carbon footprint of buildings? Although ongoing studies in Italy are already addressing these questions, why not integrate these factors into our risk targeting calculations? Would this lead to a more sustainable and cost-effective approach to seismic design? Here are the references to the studies cited in this video. Feel free to check them out for more in-depth information.